Let's talk about tonight. This is one of my favorite topics, air pollution. I remember 30 years ago or so, we couldn't even drive to downtown LA because it was so thick, it was smog. Whatever they did, it's so much better. And Dr. Reza Toossi is a professor of mechanical and aerospace engineering at Cal State Long Beach. He received his bachelor degree from Sharif University of Technology in Iran, Tehran, which is equal to MIT of the United States, and his master and Ph.D. degree from University of California in Berkeley. He continued his postdoctoral research, studied in Lawrence Berkeley Laboratory, and joined Cal State Long Beach faculty in 1981. Dr. Toossi has worked both as a research scientist and a consultant on various projects related to aqueous, aerosol, and droplet in atmosphere, nuclear safety, sensor design, air pollution modeling, fluid mechanics, and fiber optic. His current interests are conducting research and teaching courses on combustion, environmental engineering, and renewable energy sources. He has a long CV, of course. I'll make it more summarized. He has worked with government agency. He published books on energy. He has various articles in scientific journals. His current recent interest is hydrogen storage system, sorption, refrigeration, and renewable energy system. He's a member of many scientific, scholarly, and creative achievement for his work. He also had TRW Excellent in Teaching Award. We're very pleased to have you here, Doctor, and I'm very honored to have you. Please, you may start. And we're recording this.
Yes. Good evening, everybody, and thank you very much for your kind introduction. I think I have to hear this once in a while, so I forget, I boost up my image. Anyway, I'm very, very pleased to be here in the gathering of many distinguished scientists, mostly physicians, and I also want to welcome some of the students from my school that they're taking a course in the energy, and I asked them if they want to sit down and listen to us. So anyway, the topic, if you don't mind, I'd like to share my screen. Okay. Today, I'd like to talk about many topics. In summary, I'd like to talk about specifically about three types of pollutants. The air pollutants, the stuff that are coming from the combustion sources and various sources around us. And there are toxins, and lastly, I would like to talk about radiation. I'm not a toxicologist. Most of you guys are doctors, physicians, and therefore I refrain from saying too much about that because I don't want to run into trouble. On the air pollutants, we talk about different types, and specifically, I like to talk about ozone, formation of the acid rain, and finally about smog. And on the radiation side, I would like to talk about two kinds of radiations, ionizing and non-ionizing radiations that we encounter. Okay. Air pollutants are mostly from the combustion. Half of all the air pollutants come from the combustion sources. Combustion sources are like our cars, the power plants, and anything that we burn. burning is dirty. No matter what you do, as soon as you burn it, you produce this pollution. Mainly there are nitric oxide, sulfur oxide, and carbon monoxide, which in addition to a combination of these things, which we call it classical smog. The secondary pollutants are those kind of pollutants that they're not coming from the exhaust pipe, but they are made inside the atmosphere. Once the primary pollutant from the smokestack and exhaust pipe come to the atmosphere, they react with the atmosphere and produce other things. For example, sulfuric acid. Sulfuric acid is one of those kind. Ozone and also smog, those are secondary pollutants. And then toxins, of course, we have different kind of chemicals, volatile organic compounds, pesticides, mold, PVC, metals, etc., etc. We can also divide the pollutants into natural and anthropogenic. Natural pollutants are the ones that they are in the nature: dust, pollen, sea salts, ashes, smoke, particularly from the forest burning. These are all natural resources, sources of pollutants. Anthropogenic, of course, are the ones that are being produced by human beings, and mostly it comes from the fossil fuel combustion, and also they are ozone, which is the secondary kind of pollutants. As I mentioned, most of the pollutants are coming from cars. This is a table shows from the transportation, which are mostly our cars. 30% of all the greenhouse gases, 52% of all the nitric oxide, 58% of all the volatile organic compounds, or basically hydrocarbon, and 20% of all the particulate matter they're coming, from the car. So you can see most than 50%. Stationary pollutants sources are also in this category, because stationary sources like a power plant, refineries, those are burning stuff or they're cleaning stuff. So 30% of other greenhouse gases and about maybe 20% overall of other kind of gases come from the stationary sources. So the only other kinds are the industrial, what it produces inside the industries, and other sorts of pollutants. Each year, about 7 to 8 million people die of air pollution-related sicknesses. About 600,000 of them are children under 5. In the United States, in number is about 200,000 they die, and about $150 billion in the economic losses in productivity is directly attributed to the air pollution. As I mentioned, the sources of outdoor air pollution are vehicular emission, power plants, and dust, pesticide, herbicides, and wildfires. Then we can divide up the pollutants in the forms of the different kind of transport and the time that they stay in the atmosphere. For example, temporal transport are those which are coming from the stationary sources, and the mobile sources. Those are time dependent. Those are which are specifically per location dependent are the point sources, the ones that are coming from a smokestack, and also line sources, which are the freeway area sources and volume sources. Depending on the air pollution modeling, which I've done quite a bit of work, we have to sometimes consider these, the time dependency. Sometimes we can assume it's like a steady state, and that's a little bit too much to go into the detail here. I would be glad to explain more during the question and answer session. For example, one of the models I did was on the Chernobyl radioactive dispersion. I had a grant from the Defense Nuclear Agency, and basically I looked at how the radionuclide from the Chernobyl plant came to the United States. one of the interesting thing is that the plant is going over the Europe. So the first location they were supposed to hit is in the New York area, the East Coast. But the East Coast did not see the pollutants. We detected the pollutants in California for the first time. So people were puzzled. How is it that we don't see it on the East Coast, which is closer to Chernobyl than we saw it in the West Coast? And so we had a grant, and I looked at this problem, and we showed that what actually coming out of the plume of the power plant here, that is because there was not much wind at the time, and they were these were very, very hot. It has a high force, so it pierced through the atmosphere, went over the cloud, rather than staying in the stratosphere, went to troposphere, went through the stratosphere, and they were carried by the large circulations, and so that's why it avoided, avoided the New York area and sank in directly in the West Coast. So the first kind of pollutants I like to talk about is ozone. I'm sure most of you are familiar. Ozone is a 3-atom oxygen. This is monatomic oxygen. This is a diatomic oxygen, the one that we are breathing and part of the air molecule. And this is the triatomic oxygen, which is, we call it ozone. And of course, this one has only 1 oxygen. This one has a 3 oxygen, which is the 2 oxygen plus 1 oxygen. Both of these cases, they have 1 extra oxygen that can attack the material and can be very oxidizing. And that's what the oxidizing nature of the ozone comes from. The ozone, we have an ozone layer on top of the atmosphere. And this is where the ozone layer is, where they're much higher than when the planes are flying, but these are where basically hot air balloons are going about, 10 miles above the atmosphere. And then the ozone layer starts, and then up to 35 miles, the ozone layer exists. The sun rays, mainly your ultraviolet, they piercing through this ozone layer. We have 3 kinds: UVA, UVB, and UVC. UVC is the strongest one and the most dangerous one. This UVC is being absorbed by all the particles into the atmosphere before it reaching us. So pretty much we don't have to worry about UVC. UVC is basically used maybe in some hospital as a disinfectant, and killing the viruses and microbes, and I'm sure you know a lot more than I do, but those are very, very hard to work with. UVB is the one that they're piercing through the ozone atmosphere, but it's being absorbed by the atmosphere. This is the one that basically causes, if it pierces through the ozone layer, then it can cause, harm to the people who are taking sunbathing here, basically source of melanoma. It will pierce through the skin, not too much, but enough that can get to the lymph nodes and maybe cause the skin cancer. The UVA is the one that is piercing through ozone. That's the one that they're coming, and basically when we take the suntan, it will be tanning us. Pretty much when we take suntan, we are being cooked into the atmosphere. That's the flesh which is being cooked, and this is because of the UVA, and also tanning machine is using the UVA. Okay, so I will talk about how the UVA is produced and destroyed. This is what we call it, the ozone hole in the stratosphere. It is mostly in the Antarctica, where there is a cold region, and this one, through a very complicated mechanisms, maybe I can show it to you later, that it shows that when the sulfur molecules and bromine molecules, they reach the stratosphere, each of the sulfur and bromine molecule can destroy up to 50 atoms of the oxygen. And that causes, the oxygen depletion. This is the mechanism to show how the chlorine attacks the ozone. It produces ClO, and ClO attacks more ozone, and this thing repeats over and over again. And finally, the outcome is that the 2 molecules of ozone become 3 molecules of oxygen. The person who proposed this mechanism were 2 people. Basically, these are the Paul Crutzen, Molina, and Sherwood. And the last 2, they show Sherwood Rowland. He's a professor at the UC Irvine, and he's retired now. And he got the Nobel Prize for this mechanisms in the 1995. What is destroying the ozone? Basically, main culprit is to believe the CFC, chlorofluorocarbon, and the halons. Chlorofluorocarbons are the non-toxic, inexpensive, energy-efficient substitutes for the highly toxic and potentially explosive ammonia that they were used up to recently in the refrigeration system and also as an insulator for the houses. After they found out those are, cannot be used, then we use the CFC. They're marketing under Ferion or R12. Some of you might be familiar with that, which is widely being used in the fire extinguisher, refrigeration system, and aerosol spray cans. So the spray cans that you're using, using the makeups, those are pretty bad for the ozone layer. So please avoid those. So following the Montreal Protocol, then the use of CFC eventually was banned. And no, we don't use the CFC. The half-life of ozone in the atmosphere is about 50 years. That means it takes several hundred years so we can repair this, but our atmosphere is on the way to recovery. So it's getting better and better, but we still have a long way to go. These are the source of this. Halon is what you use in the fire extinguishers. Every time we talk about fires, which was part of my research, fire spread, we are looking for the bromine, and that is what distinguishes fire. We have not found any substitute for bromine, so we are still using those bromine today in the fire extinguishers. Halon 1211 is a liquid form. Halon 1301 is a gaseous form. It's too much of a detail, but those are the ones that are used today. As I mentioned, they saw the early warning signs of the ozone depletion over the Antarctica. This is the original paper that I mentioned to you. And you can see the Molina and Sherwood are from UC Irvine. And that's the article that they won the Nobel Prize in 1995. This is the list of those materials that destroy ozone. You can see CFC, chlorofluorocarbon 11, 12, 113, 114. There are a whole bunch of them. And you can see these are the uses. And look at the half-life of them is 60 years, 13 years, 90 years, 50 years. So these are taking, that means, and 60 years it takes, so half of them is being naturally destroyed. Another 60 years, that means 120 years, that means half of the half is destroyed. And that's what the half-life means. And here it said that these are where the problems are. You can see CFC12, that's the one we were using it, because it has a relatively short half-life, but it causes most of the ozone depletion, and it's 30% of what has been used in the United States up to recently. And these are the halons. One of the ozone is causing fatigue. You doctors, you know better than I do. I don't dare to talk about what the ozone does, but most of the problem associated with the reduced immune deficiency is coming from the ozone. In the United States, in California, Pasadena is where the maximum concentration of ozone is, in Pasadena. So that's the area that we have to watch out. Ozone is the cause for necrosis, what it causing, that the plant, to discolorate and browning of the plants is mainly due to the necrosis too. The second problem is the acid rain. Acid rain refers to any kind of acid precipitation, such as acid fog, acid snow, acid mist, you name it. We all lump it together and we call it acid rain. It doesn't have to be a rain. It can be snow, or it can be inside the fog into the atmosphere. And that eventually into the aerosol that they're falling to the atmosphere, and maybe eventually they become liquid and like acid rain. The main components that are responsible for the acidity of these particles are mainly oxides of sulfur and particle. We measure the acidity by the pH level. pH of the water is neutral, is 7. And as we go in this direction, the pH drops, and that makes it become more and more acidic. Among them, coffee, banana, milk, and wines are acidic. And the most acidic, of course, is the lemon juice. On the other side of the scales are like the eggs, and any hair removers, and the solvents. These are all basic. So what are the impacts of these? They endanger plants and marine life, degrades the material, and they affect the lakes, ponds, etc. in the adverse way. One question always comes up: what does the role of the material that make up the lake? Sometimes the lake are made of limes. These are like scrubbers of the sulfur dioxide, and they neutralize the sulfur. So, but it actually kills, a lot of the algae and so. So sometimes when you see a very clean lake, is not really clean at all, but it means that there were material that the basin of the lake has neutralized the acid. And that's what causes, the clarity of the lake. An example of the acid precipitation is in these statues. These are the statues made of porous sandstone. It was created in 1702, and it's being installed on the entrance to the castle at Herten, Germany. And the left photo shows the picture taken in 1908, and the right picture shows the same place, the picture taken at 1968. That means over the matter of 60 years, when we use more and more coal in Germany, and we burn the fossil fuel, and we use a lot of the sulfur, you can see what the sulfur has done to the statue, which remained pretty much intact for 300 years. In over 100 years, 60 years, it has come to this. And now how it looks, I don't know, I haven't seen it. Okay, what is the smog? Smog, first of all, is a made-up word. We don't have such a word as smog in English language. We made it up from the combination of two words, smoke and fog. We just put it together and became smog. And now, of course, everybody talks about smog. It's a smoke and fog. We have two kinds of smogs. One is a classical smog, and the other one is a photochemical smog. So we don't want to, we want to differentiate this between these two. Classical smog is when the plume of sulfur oxide and particulate matter, they generate and combine due to the combustion of coal. This is a picture of London in the October, I think December 1952, between the days of December 5th to 9th, over a matter of 4 days, haze is covered London. This haze comes from burning of a lot of the coal at that time. And then there was an inversion layer that I explain in a second, that they covered over the city of London. So all the soot particles, carbon particles, and sulfur dioxide particles was trapped very, very close to the surface. And the air was stagnant, no wind, high sulfur content. The winter was cold. It was a low inversion layer, all the recipe for a disaster. And indeed, that disaster happened. Over the period of 4 days, 12,000 people were killed in the city of London. People could not transport, the elderly, they could not move, and they were trapped there, and they couldn't evacuate London, and 12,000, and they say up to 30,000 people have killed over those. This is the low estimate, you know. So this is a classical smog. Basically, it's a soot particles, the particles coming in. Photochemical smog is something totally different. It's a question of the ozone. The ozone plays a huge role, and I will explain later how the photochemical smog is produced. This is Los Angeles, the city that in many of air pollution books, there's a chapter called Los Angeles. So we are famous or infamous, if you want to, for this smog. You can see there is a inversion layer. That's what you see when you look out of your window at the horizon. You see a orange, layer, and this orange layer is basically nitric oxide, and that means there is a inversion layer there. Inversion layer, I think, is the next layer. Yeah, it's right here. Basically, under normal condition, the sun heats up the earth. Okay, sun is the heat, the hot, the earth becomes, the air over the air becomes lighter because it's hotter. So the air rises and it goes, pierces through the atmosphere. If there's no inversion layer, they become colder and colder eventually and goes to the upper atmosphere. This is the normal condition. Under temperature inversion, you can see that the is exactly the opposite of this. This is when temperature increases as altitude increases. So rather than temperature decrease, temperature increases. It hits a layer of the cold air, and then as you go hotter and hotter, higher and higher, the temperature starts to become cooler and cooler. But here, a layer of cool air is trapped between the two layers of the air. It's being sandwiched. This is the place that the air cannot diffuse inside. And so this is the inversion layer, and that's what causes all of this problem. If you look at the profile, you can see on the surface, the temperature is warm, the hot air decreases during the day and eventually decreases all the way and until it leaves the atmosphere. In the inversion layer, the air layer is basically cold, but it rises the temperature and eventually reaches the warm layer and they go to the upper atmosphere. This is often the case in the clear, windless nights. The sun sets in the evening due to the cooling, radiative cooling of the Earth's atmosphere, and usually coupled with the lack of, as I said, lack of the wind, and that's what causes the inversion. So, what happens here We have the sunlight, basically goes, attacks the fog that we have, okay? And we're producing nitric oxide. The water vapor from the atmosphere is also available. The best way I can explain this is to imagine a pot that you want to build a stew. To build a stew, you need the lentils, rice, and all those ingredients. You put it inside the pot. The pot is made of metal, and then you add the water. You have the heat from the bottom, and then you put the lid on top, and you wait, and everything burned out. We have this hot situation in Los Angeles. That's why Los Angeles is very famous. In Los Angeles, we have a lot of ingredients. The ingredients are all the cars. The cars produce sulfur dioxide, nitric oxide, they're present, so we have all the ingredients. We need to have a pot. We have the pot here because of all the mountains which are surrounding us. The mountains surrounding us will contain this emission, doesn't let to diffuse. That acts like a pot. We need water. We are next to the ocean, so we have a lot of water. We need heat. We have a lot of heat. We have a lot of sunlight. Rather than heating from the bottom, we're heating from top. Everything else, we need a lid. That's the inversion layer. So now we have all the ingredients inside this pot that we let it brew, and after a while, we have what we call it the smog. And this smog is what's happening in Los Angeles many times. Now atmospheric air in Los Angeles is getting better and better, thanks to the Air Quality Management District in Southern California, that they have, by these regulations, all this smog change and things like that, the air is becoming cleaner. Here I'd like to talk about something called air pollution index. Air pollution index is something like a stock market. In the stock market, like a NASDAQ or New York Stock Exchange, you don't have a particular stock, which is called NASDAQ. What we have a whole bunch of companies, okay, like 60 companies or so, that we think they are the most critical in the health of our economy, and those are making up a combination of those, making the NASDAQ Smog Exchange. We said, let's say 10% of Apple, 5% of Amazon, 20% of this. We call it the NASDAQ. So that's what it is. The air pollution index is something very, very similar. We look at all those things which are important. What are important are the sulfur dioxide, ozone, carbon monoxide, nitric oxide. All of those are the important contributors, to the air pollution index. So we take certain percentage of each of these, we add them together, and we have an index now. We have arbitrarily set the index to 100, and the 100 is the threshold between good and bad. But good and bad are relative. If you go between 100 to 150, okay, we say, well, is pretty okay. General public are not much affected, okay? But if you go the index, to 150 to 200, then we have to say some people who have asthma, they experience the health effects. Sensitive people should not stay too much into the sun outside. If you go to 300, we call it very unhealthy. At that place, the elderly have to stay home. That's the announcement. We shouldn't stay outside. We shouldn't exercise too strenuously. And when you go to 300 to 500, we call it hazardous, which is the health warning of emergency condition. Entire population is likely to be affected. And maybe there are instructions not to leave the house more than a few minutes at the time. On the other side, between 50 to 100 is acceptable air quality, it's good. 0 to 50, we call it very clean air. Okay. In the United States, in the Los Angeles, I'm sorry, we have several days, depends on the year by year, maybe 10, 12 days of the unhealthy air, okay, in this region fall. And most of the time we are falling into this 100 to 150 level the rest of the days. These are the data which are being published daily. I know many of you are interested about Iran. Okay, apology to all those people who might find this part of the presentation not quite to their interest, but it might be. Air quality degradation is a major problem in Iran's major city. A result of rapid and unchecked urbanization, high population density, inefficient use of non-renewable energy, low quality, high sulfur containing coal and other fuel, an aging fleet of gasoline and diesel vehicles, limited transportation capacity, proximity to active industrial sites, or the industrial sites are near the cities, and most of all, we have a very unexperienced, disqualified management that are running the business of the air pollution. I have some stories myself, which are not very pleasant. Air pollution is a cause of about 30,000 estimated deaths per year in Tehran alone. The problem is especially severe in winter, and when we have a worse condition. We have a inversion layer, low inversion layer over Tehran. That is, you're burning a lot of cars, and then it piercing through all the heat, and the surface becomes colder than the heat, which is below a cold layer, cold layer. So that's a effect of the inversion layer. Average concentration of hazardous airborne pollutants, most of the time is 150 and higher, the pollution index for most of the cities in Iran. In Tehran, it can reach 200 to 250 easily. I don't have any data on that. The World Health Organization that in 2018 put the Tehran into categories of most polluted city in the world. The World Bank in 2018 report said that city accounts for 4,000 to 12,000 deaths due to the air pollution. And these are the data I took from a paper that I read by Dr. Madani, that most of you know, that he's done a lot of work, and he published a paper and gave some of these statistics that I give you. In addition to this, some of you might remember the dust storm in Tehran. That was in June 2014. Dust and salt storm is the result of the increased dried wetland that deforestation, soil erosion, and desertification. These are all the result of these dust. You can see that this dust is huge. It covers the whole city. In 2014, the wind of 110 kilometers per hour, frequent dust storm, especially in the Sistan and Baluchistan, that they're coming from directly from the neighboring Afghanistan and Pakistan. That's their gift for us. In 2016, Zabul in Sistan was named by the World Health Organization as the most polluted city in the world. That topped the Mexico City and New York City at the worst times. Okay. a little bit, the air pollution is not limited to outside. Dr. Madani, how much longer do I have?
As long as you wish.
Till about 11:30 p.m.?
Yeah, yeah.
Okay. So,
Usually about plus minus an hour and then questions.
just tell me how many minutes, and then I will trim my presentation.
How about my like 25 more minutes?
That's fine. Thank you.
Thank you, sir.
So a lot of building, they say about up to 3 million building in the United States, they call them sick building syndrome. Basically, all of the buildings are sick to a certain extent. These are very sick, 300 of them. We have sources of pollutants everywhere. We have it in our bedroom, from this even air sanitizer. We have it coming from the showers, inside the kitchen, in the dryer, washer dryer, in the fireplace, in our basin. So there are indoor air pollution all over. Up to 1960s, we did not have this term indoor air pollution. When we were talking about the pollution, air pollution, we were talking about the outside air pollution. That's when, for the first time, they noticed that we have to be worried about what kind of material we use in our housing, and what to burn, and all the stuff. And that's when EPA, Environmental Protection Agency, was established, and they basically established this term indoor air pollution. They made a distinction between outdoor air pollution. Okay, toxins. Toxins, you probably all know, but what is toxic, what's not? I'd like to make a quote from this gentleman. I don't know how many of you know him. He's a Paracelsus. He was a Swiss physician, a lay theologian, philosopher of the German Renaissance, and basically said all substances are poisons. There is none that is not a poison. The right dose differentiates a poison from a remedy. And I think most of you doctors agree with this analysis. I believe my dad died because he drank too much water. And he thought water is good for him. So he just drank water and water and water. And basically, he washed his body out of every nutrient that's possible. Anyway, that's my thing. Okay. So where are the toxins? Basically, there are three toxins that are everywhere in our food, in our water. I don't waste your time to tell you where it is. I'm telling you there's no place that's not. We have so many. But this statistics might be of your interest too. 5 million deaths as a result of environmental chemicals in the United States. Toxins cause chronic fatigue, depression. These are what are linked to the environmental toxins. And there are things that are neurodegenerative. These are the diseases that attack the autoimmune disease. They have increased, ever skyrocketed. I can tell you from personal experience, and have linked some of these to the use of the various pesticides that they use in the agriculture. Oh, that's a sick building syndrome, and a short list of the toxins are the I think it's polybrominated diphenyl ether, PBDE. That's in fire retardants, eventually, virtually in all of the household products. There are heavy metals that exist in some of the fish we eat, and in the solvents, hair dyes, and PVC, which is used in the flooring and water pipes, etc. In addition to that, we have radon problem. We don't have radon problem in the West Coast. It's a problem of the East Coast, and I talk about it a little bit more. These are the ionizing radiation material. So biological contaminants, are things like bacteria, mold, pollen, viruses. These are all contaminants, and the condition under which they grow, like a mold, humidifier, water storage, ceiling tiles, carpeting. These are all over this stuff. Radon, as I said, is a colorless, odorless gas, primary source of air pollution, and it is a ionizing radiation. These are the major household products. This is basically the lightener, paints, fertilizers, pesticides. These are the propellant or aerosol, and finally the solvents. So we have it all over the house. If you can store it outside the house, so much the better. Okay, a few words about radiation. We had many talks here before talking about different kind of radiation. There are radiation all over us. Radiation is over all the wavelengths in the sunlight. Some of them are visible, some of them are ultraviolet, and we have a range. And then we have radiations which are very penetrating, like the X-ray, gamma ray, etc. Anyway, we can divide it into two sections. Non-ionizing, these are visible, infrared, microwave. They do not cause the molecules in your body to ionize. They're either background. You have background radiation, which can be the radiation that we get from sun to get tan. Also, they're man-made, like the radiation that is anthropogenic. You get through exposure to the ultraviolet, or the sunlight. The ionizing radiation are radiation with a high frequency, lower wavelengths at the other range of the spectrum. The most dangerous one are the cosmic ray. These are the radiation at a very high elevation. The pilots of spy planes, those are the ones that they fly at very, very high. They expose to a lot of gamma ray, cosmic rays. Also, the astronauts, those people that they go on the rocket, those are also exposed to the cosmic ray, especially if they stay in the atmosphere for a long time. For that reason, the pilots that they fly in a very, very high elevation, they're only limited to only a few hours of flight every week. Then we have gamma ray. Gamma ray is, again, very highly penetrating. X-ray, you're all familiar with it. It penetrates through the body, stops by the bones, and basically you have UV, we have different kinds of it. And we have to just worry about the UVC, which is the part which is ionizing. And that one is the skin cancer. And again, we have both natural sources of cosmic radiation, of ionizing radiation, and we have like a radon. Radon is one of those. It's natural, but it is ionizing. And then we have a man-made radiation that we're producing. And that comes from the power plants, from the nuclear accidents, and that's a different story. This is how the radiation penetrates different substances. Alpha radiation, these are the basically the if they penetrate, just a piece of paper can stop them. Beta pair, which are the electrons, they stop by a thin place of maybe wood or something. X-ray is stopped by the lead, and that's what we cover ourselves. We don't want to be exposed to it. Also a piece of the iron, thick metals. But the gamma ray goes through all of this, and the neutrons are the one that even more penetrating, and the only way you can stop the neutrons is through the material which have hydrogen in them. Water can stop it. Concrete, also has a lot of hydrogen in it, and that's a source of pollution. Those are the ones that can stop this thing. Otherwise, you cannot stop them. As I mentioned, this is the alpha particle, which is the nuclei of the helium atom. The beta particle is just one electron. The gamma ray is radiation, and then neutrons, which is one atom of neutrons. So there are different ways that we measure radiation. That might be of some of your interest to you. That's why I put this slide, because there's some confusion how we present different source of radiation. When we talk about the becquerel or Curie, okay, the one on the right is a metric unit. The one on the left is a US unit. Okay, when we talk about the becquerel, means the disintegration. So if you have a source and we measure once in a while, one atom pops out, it's been thrown out, that one is 1 Curie. Okay, 37 billion Curie is very, very small, it's called 1 becquerel. So that's the source, radioactivity of the source, how effective that source is. Now the source that's coming in is being absorbed by some material. First of all, how much of this is being exposed? That's measured by the Röntgen. Okay, that's about 1 Curie per every kilogram. What is absorbed is called RAD. RAD does not stand for radiation, it stands for radiation adsorbed dose. That's a RAD, radiation adsorbed dose. And then the SI unit of that is gray. And again, that is how much being absorbed by your body. So larger surface area, you absorb more stuff, okay? The higher intensity, you take more Curie. So these are different. And then the damage that caused depends what part of the body is being exposed to the radiation. Obviously, radiation that hits the bones, it has less damage than if it hurts to the muscles of your heart. I won't talk too much in the presence of so many doctors are sitting around. And then finally is a sievert that shows them the damage. That depends on the material, biological material. So if you're talking about the damage to a statue, the sievert does not make any sense, okay? Then you have to look at the adsorbed dose, okay? Anyway, that was my presentation. I'm sure there might be a lot of questions. I'm here. Hopefully you learned something from this.